Over to you. So, greetings everyone. You have joined the event being hosted by the Silicon Valley chapter of the IEEE Computer Society. I'm Vishnu Pendyala, the chapter chair. As the largest chapter in the Silicon Valley section of IEEE, we are proud of our 3,500 subscribers in our mailing list. We also have a robust Twitter following of more than 12,000. We hold a unique position due to our strategic location and the wealth of expertise available to us. And we are also able to uh, leverage the expertise from all over the world thanks to the virtual mode. So today's talk will be on sustainable AI. We all know, we have been hearing a lot of news. AI models, particularly the large language models, can threaten sustainability. So it is quite apt that the co-author of one of the top-ranking large language models on HuggingFace leaderboard, Llama 3 and Llama 2, Soumya Batra, addresses the issue of AI and sustainability today. So listen to all about it in this talk that she kindly agreed to give to the chapter audiences. Soumya Batra, co-author of Llama 3 and Llama 2, has 11 years of experience in natural language processing. Her journey spans from her master's at Carnegie Mellon University to industry roles at Microsoft and Meta. She has worked across classical machine learning and large language models, focusing on conversational AI, multimodal AI, data efficiency, evaluation, and safety. She has contributed to products like virtual assistants, reality labs, and the Llama models. Soumya is currently an independent researcher exploring sustainable and energy efficient AI models in India. She's also an advisor to an edtech startup. It's in stealth mode right now, and founder of Tech for Good India initiative, which builds tech products for societal improvements in India. She was recently listed as a H20 top 100 AI thought leader in 2024. Uh, Actually, H2O top 100 AI thought leader in 2024. So before I hand over to the speaker, just wanted to remind you that you can post the questions on the chat window and I will relay them to the speaker. Over to you, Soumya.
Thank you so much, Vishnu, for inviting me and the awesome intro. And very happy to be here. So yeah, I'll just start sharing my slides. Can you see them?
Yes.
Okay, great.
Perfect.
Yeah, so as we know that why when I chose the topic for my independent research, or even why we are talking about it today, is because we are clearly in an arms race with AI, right? Between companies and between even countries. So while we do that, there is a significant environment impact that is going on in the background. And I think that is important to address as well before it becomes a big problem. So wanted to explore this field and want to share some points on that. Yeah. So again, let's first define what we even mean by sustainable AI when we use this term. And the best way is to just ask a language model, right? So I asked Llama, tell me what sustainability means. And it says that, yeah, we want to develop AI that maximizes benefit while minimizing the overall societal harms. And so what we are saying here is that since a pretty long time, the LLMs or the large language models are clearly revolutionary technology. They have a huge potential. We know that they are powerful. In fact, we know that they're changing our world in ways we don't understand. And in fact, we definitely know that there are going to be applications that we haven't even thought of yet because of the fast pace of change. But that having said that, that is the reason that it's developing. Such a powerful technology is being developed so fast, also implies that it needs to be developed responsibly, so that we can take benefits from it and while minimizing the harms. In other words, we don't want to end up in a matrix scenario, right? And typically, when we say sustainable AI, there are two components of it. One is energy efficiency, and the other is safety and fairness, where the responses themselves are toxic or causing real world harms. An example for that would be like something that's already unfortunately started happening, where people are creating deep fakes and collecting private information from unsuspecting users. And sustainable AI is sometimes also used in the sense of using AI to identify climate change solutions, which in my opinion, I find a little bit hypocritical. But yeah, so here we are talking about the sustainability of the AI while developing them. And in particular, since these 2 points themselves are large topics on their own, we will be focusing on the energy efficiency of these models today. So again, the question, should we even care about energy efficiency, and or is it blown out of proportion? Should it even be a goal? And the thing is that one is it has huge environmental impacts, right? The AI that is being developed in Latin America, in one of the countries there was, so AI has both excessive power and water demand. So one of the places in Latin America, there one of the companies was trying to set up a data center, and the people, they had to reject it because they didn't have enough water for their citizens, and the model was water hungry. So we don't want to live in a world where we are, where there's no water for people, but because the water has been redirected to AI. Coming to electricity demand, it's expected that the data centers will double their demand in just 10 years. And that's almost like, having a electricity demand equivalent to a California state. So we would be adding another state with the same capacity, with the same resources. And thirdly, it's expected that the AI is going to cause air pollution problem as well. And these issues, so do want to say that anything, these estimates, all of these are estimates, because one uh, one factor that amplifies the problem is that the companies do not release this data. They do not release how much energy is being consumed or how much water is being consumed. So these largely come from estimates, which is why you might see different estimates across different news articles as well, different numbers. So again, like appealing to the one humanity principle, that so far, at least till we go to Mars, we just have one Earth, and we are the whole entire humanity is connected. So you cannot just export away the problems. And that's why, like, we should be doing a part, like while we develop these technology, why not do it in a more sustainable way so that the future generations can enjoy it. So I like this quote that from software world, that yeah, that leave the code better than how you found it. So similar to that, I think that can be applied, for every aspect in the world, that just leave it better than you found it. Secondly, the cost. So coming to the capitalistic view, certainly if the energy demands of training the model or running inference on the model is low, then it would cost less to the companies. right? Like the DeepSeek is a very good example of that. It cost, near zero to consumers, and huge, much, greater, like 100x margins to DeepSeek compared to, say, OpenAI. And it became the #1 app, right, recently. So it's also good business, basically, building energy efficient models. And over the years, we have also seen that consumers are willing to spend a little extra in other sustainable brands such as clothing, fashion, and so on. So we can expect that this trend would also apply to AI models in future if the cost difference is not that much. And finally, we think that probably these models are more reliable because they might have lower complexity. They may have lower, small number of layers. They should have, that would be an expectation, that may be smaller. And so it would be easier, it should be easier to maintain them. And finally, it's just an interesting problem to solve, right? Like if we are saying that scale makes everything better, then where is the next class of challenges? Maybe now we should focus on learn rather than throwing all data at the model, brute forcing our way through it, finding algorithms that can learn from small amount of data, similar to how humans learn, with different sort of learning algorithms and perhaps even different hardware. So just looking at now, just want to share some statistics on how bad the problem of, how harmful the environmental impacts may be from running these models. So these are some, statistics from just like published last year. And what we see is that, okay, so one thing is expected that the data center let's come to energy first. And we see that the demand for electricity for data centers will just double by 2027, right? Sorry, from 2% to, it's just going to go to 4%. So that's one. Then secondly, we see that the most carbon, so if you see the figure over here on the right, we see that the model with the highest, the bigger the model, the more polluting it is. That's a general trend we are seeing. But also that if you compare the most carbon intensive model with the least carbon intensive model, the factor is of about 6,900 times, which is like 4.1 miles driven on an average vehicle. So that tells that just by choosing the kind of model we are interfacing with using, the level of impact it can have on the carbon emissions. And coming to water, so great study done by Charlotte Wren, and he's been working on this for a decade or so. So they find that the water consumption, so a lot of the times when we think of energy efficiency, we only think of power. And in fact, it's kind of expected that power is probably not as big a deal. Maybe we can move to green resources sooner. We could move to nuclear energy sooner and it would be solved. However, water is an issue that we can't just solve, right? Like we don't realize that these data sets are also very water hungry and clean water hungry, that too. So water is a shared resource, it's a scarce resource. And that is something that we cannot, that we just need to reduce in order to work with it. So here in this study, what they find is that the water consumption varies by location. So colder regions will have likely less water requirements compared to warmer regions, because you're also accounting for evaporation and so on. And again, to put it in context, these are inference numbers, by the way. So even if say you say a small model for inference, but the inference costs are, consuming this much water, then we have to think that whether, like where maybe even going smaller doesn't have that much of an impact. So like imagine like 10 to 50 queries, just 10 to 50 queries, they require about one small bottle of water. And then you have, and just imagine like you have a billion queries every day in ChatGPT. So you can imagine how much water is being consumed just for inference alone. So let's look at some of the solutions for maybe, how we may achieve the energy efficiency. While noting that even if we did achieve, we may still not be able to have, as much climate impact as we wanted. So basically at two different scales, let's discuss it at industry scale and what we could do as individuals. So at industry scale, one, definitely there's a green energy revival. Microsoft, there was, news around Microsoft buying the 3 Mile Island deal, nuclear energy seeing a resurgence, and so on. So there is one factor. Obviously, of course, the nuclear waste and proper handling of it is, and making these power plants efficient is another story. But essentially, that's one way that the big companies are looking at managing this problem. And then definitely like data center redesign. So interestingly, even for the current models, but just by doing data center redesign, you could still see pretty significant improvements without needing a new energy source. And again, the energy, like this is, so how what would redesign consist of? Maybe moving to an energy efficiency friendly location. But it's not as easy as as you might think, right? Because maybe, so there are competing factors. Say if you are trying to optimize for both energy and water, then both of those are competing with each other, because the region that has more sunlight will have better energy efficiency, but for water, it will probably also be consuming much more water than, say, if it was in a colder place. And then, of course, how the local communities respond to it, what's the infrastructure, and so on, also play a role. Then certainly, like there is hardware that is more energy efficient. That's something that the companies are doing, moving to more energy efficient hardware. Then doing energy audits, wherein you measure which parts of the day or which cycles during the training are consuming more or less energy, and then optimizing your workflow accordingly. And then finally, like optimizing even software for improving GPU utilization. We saw that like with flash attention, with many optimizations that DeepSeek did, for example, at the hardware level. Llama did previous to that. So those things help with, like, the more you're utilizing the GPUs, the better it is for energy efficiency. And finally, there is a new welcome push from the industry to build metrics to measure energy efficiency. And we know that whatever we can measure can be improved, right? So the current thing is that we don't even have metrics, but the industry is working on building metrics that can measure the energy efficiency, and that's something that they can optimize for. Although again, one important thing here as well is to be transparent. We do need industry to be more transparent about these metrics, at least. So coming to individual level, what we could do by how we could build or use more energy efficient models. So again, going back to measurements, there are leaderboards like ML Energy and Puff Leaderboard that ranks the models based on their carbon emissions, and you could choose you could, and I would encourage to choose models based on their carbon emissions with everything else being equal. So that's also a way to encourage, more sustainable models. Code Carbon is another cool software package. So it's a Python code basically that you can embed in your code, and it will track the CO2 emission from your code itself. And again, like gives suggestions on maybe, moving to a different data center and so on to reduce the impact. So there are some like free ways that you can use now to either use or build these sustainable models. Secondly, like quite a big part, using small language models. So we don't need necessarily large models for every problem. And in fact, it could be more cumbersome to just use these large language models for every little, basically for every problem. And since there are multiple optimizations by which we can achieve a small language model, let's look at this topic into a little more detail. And again, when we are saying SLM, what does it mean? Can we define it in terms of the model parameters? Because that's what it sounds like, small language model. That may be a reasonable thing to do. And again, let's ask different LLMs, what do they think? So, oops. So the issue here is this is an interesting problem we see. So even when we ask the language models, what do we mean by small language models? There is a confusion. The range is from 1 million to 100 million to 10 billion. So that's clearly not, I think that's not a good way to define the small language models either. And some of the models, they've created different definitions like giant and extra large, whatnot. So by which definition, again, Llama and all will be called giant models, which of course we don't do. So, and there's a reason like why this is happening, because I mean, the technical reason is they're uh, repeating what they see in their training data and outputting it. But what's in the training data is the confusion. And the confusion is because, I mean, if you think about it, even like 2 years ago, these models were considered large, right? Like the ones that had a few hundred million parameters. And maybe according to some definition, now these will be considered small language models. So that's why just basing it on number of parameters does not help. And yeah, I mean, if you compare it to today's models where the context size is even 2 million tokens, then yeah, this wouldn't fit. So again, what exactly it is? So a better way is to define it with the intent, right? So it's not, I mean, one issue with defining the models with respect to the the number of parameters is that you can just go to 1 billion even. You can keep going smaller and it doesn't, like, where does it stop? We need some other constraint as well. And the constraint comes from its usage, which means that, which is that, okay, we want to make our model as small as possible, but we also want it to be as performant, or within limits performant to an equivalent LLM, that, or at least a previous generation LLM. So these performance metrics constrain it, and that's when we that's how we can define it. Typically, we also again wanted to fit on our device, and they typically, when we talk of small language model, we uh, we are thinking of specific tasks rather than a generalized model like an LLM. So last year, in fact, saw the beginning and rise of SLMs, and since February, in fact, it was called 2023 was the year of LLMs, 24 was called the year of SLMs, and we'll see what 25 is, probably RLs. So other than sustainability, is there any reason that SLMs could provide us? Yes. So there's a increasing demand for SLMs. They are the best. Even the biggest advantage that SLMs give is that you can host them in your own servers. So super useful for defense, military, even some enterprise use cases where they don't necessarily want to even store data in air-gapped cloud. So privacy is a big one. Then we talked about cost, and it's of course more efficient. It's also usually easier to customize these models because you're doing it for your specific task. You have access to the data, and where how you want to tailor it. And the SLM market is expected to be 20 billion. It's 8 right now and 20 billion by 2030. Contrasted with LLM market, which is expected to be like 32 billion. So quite close by. No, I mean, I'm not talking about the overall market, but at the foundational level. So I think this is quite, I could see that, like if we had smaller models at reasonable performance, you would likely prefer that rather than dealing with the memory and memory management and other issues with LLMs. And finally, they are a necessity for you cannot just host a on-device LLM. They have a very small memory real estate, and in fact, a lot of the devices that have intelligence right now that we are using, they are based on a smaller version of the larger model. Like the Meta glasses, they use a quantized version of a Llama model. That was the reason why when Apple came up with the language models on their device, there was excitement, even though it could be considered late because it was on device and small. And again, so now just coming to how we may build these SLMs. So mainly two techniques. One, you take the existing LLM and compress them, or we build them from scratch. So there are three main techniques. We'll just look at each of them briefly. So distillation, pruning, and quantization. So let's look at the compression techniques first. So pruning. And in the compression techniques, you're basically starting with an existing large language model, say a Llama model or an open source model, basically, and reducing its size, compressing it into a smaller model. So one of an effective technique is pruning. Pruning, you are essentially, like as the name sounds, we are removing some of the connections. So there are two main ways, structured and unstructured. And when we say we're removing the connections, what it really means is that like in code or in math, we are basically removing values from the weight matrices that are connected to these neurons. So in case of structured, what happens is that you take a group of weights that are close to each other and decide to just keep one, for example. So you make a grouping of say 4 and you keep one. And by that, so you are doing pruning in a very structured way. So it does not matter what the values in those group are relative to the values, say, in the rows. But it only matters that in the group, maybe you pick the weight with the highest value and so on. And in case of unstructured, yeah, you just basically have a global rule where you say that, hey, I want to keep or remove X% of the weights or activations. So the advantage with structured is that, so one point to note here, that just by removing the pruning, you're not going to get energy efficiency automatically. We do need to move. So, and that's because of matrix multiplication, right? So typically a maximal operation is done in a generalized way, where you're just multiplying the rows and the columns and whatever you're getting as an output. But we need to move to a sparse, so that would be generalized matrix multiplication. But we would need to move to a sparse mathmal operation, where most of the values are 0, 1, and we're just multiplying the other sparse values. So combination of pruning followed by sparse multiplication mathmal will help run and train faster, or basically run the model faster. So with structured, you get the benefit with just the generalized mathmal itself. However, with unstructured, you would want to move to a sparse mathmal. Okay, then coming to knowledge distillation, here, and again, like these techniques have existed. They are not like new LLM techniques. These have existed before for different AI models, but they have now become much more relevant in the context of LLMs as well, and much more impactful. So knowledge distillation, there are many ways to do knowledge distillation, but the key idea is that you have a big teacher model. The big teacher model in this case is the LLM, and using that, either you generate some data through this model and use that data to train a new student model of your choice of architecture of your however many layers you want to put it. You select that, or you use the same training you use. So that would be a synthetic way, or another way could be you can use the same training data, get the labels from the teacher model, use those labels to train the student model, and so on. So the idea is that you're basically transferring or distilling the knowledge from the teacher model to the student model by with some form of, with a percentage of some training data. Yeah, again, like there are also many different techniques with it. There could be like curriculum learning, where the data, you're strategic about the data that you're using to train the student model, where every data point is harder than the previous one, so it only learns the differential knowledge. With iterative learning, you would do this in an iterative loop. You use a kind of student model to generate different data, get it labeled with teacher model, and then train another student model, and so on. A lot of, I would say, many like different, even many LLMs in some way, they are trained after they are pre-trained in their fine-tuning stage. They are trained in a sort of iterative learning as well, and that has shown to be beneficial even for LLMs. I mean, like not just SLMs. Yeah, so knowledge distillation is quite a powerful technique, and its advantage is that you can choose the architecture of your student model. You can make it as small as you want. You can define the number of parameters. You can, make it as you can give it the shape and structure that you want. But the problem with it is that one, you need to have, at least initially, you need to have the ability and some compute to be able to run the teacher model, and it does require non-trivial amount of distillation training data, whether it's generated synthetically or it's true, or it's like collected training data. So finally, coming to and yeah, just one more point, but of all the techniques, knowledge distillation definitely has the highest impact. Coming to quantization, here you can convert, here basically the model weights and the activations can be converted from a higher precision values into lower precision formats. So typically the FP32 is the original format, and then they can get converted to FP16 or even int 8. So just like purely doing this can cause some accuracy degradation, as you can imagine. So there are some other techniques now where, like an improved techniques, where you can quantize while save, while if you to create that balance between accuracy and memory footprint, what you can do is quantize while saving the model, but at the time of inference, you dequantize them and like run it. So inference is not going to be fast, but at least this will take care of the memory footprint. So let's see how do these models even perform with respect to the base language models that we train them on. So NVIDIA had tried this. So what they did, they trained, they quantized and they pruned and distilled. They took a few of the LLMs, 8 billion models basically from Llama, Mistral, Llama, and then they trained their smaller versions. There is a caveat that they did, after pruning and distillation, they also did alignment. So that's a factor there. But interestingly, it was able to achieve SOTA, and it was able to beat these the best base LLM that these were actually trained on. So that was quite interesting. Finally, coming to this section was how we can go from existing large models to small models through different optimization functions. And now how do we build, how do companies build SLMs from scratch? So here's the interesting thing that, yeah, of course, LLMs are in pure terms, of course, the best LLM is much ahead of the best SLM. And if they weren't, we would not be training LLMs, we would start training SLMs. And it's, of course, largely because of also scaling laws. But the interesting thing to note here is that usually usually an nth generation of SLM is able to beat the previous generation, right? So here, if we'll see some models that are like the smaller ones, they would be better than, like the Mistral small is better than the Llama 3. So that is quite an interesting find, that you can probably get performance from the previous generation. Same like when Llama 3.3 was released, its text-only 70 billion model had similar performance to the 3.1, the biggest 405 billion performance. So that was also quite promising. So when we look at this, a question arises that what is driving their performance, even though they are smaller in size and the scaling laws hold. So one is, this is a very established fact now, that the quality of training data is super important. There's been studies that have shown that if you, in fact, put some clean training data and some junk training data versus you just put clean training data, so the model that is trained on just the clean data works up to 20 times better than the one that was trained on both. So in some sense, the dirty, the unclean junk data is causing much more damage than adding clean data. So again, which goes to then quality over quantity. So as we saw, when Phi had first come out, that was a great observation. Phi was quite good in performance, and their reasoning was yeah, they did take high quality curated training data, so that helped them. And then that's one. Then second, maybe that we are still using the huge training data sets and trained beyond the chinchilla optimum. So Quen 2.5, I think it's trained on 18 trillion, much more than the models at the time. And they train beyond the chinchilla optimum. So that also helps, right? Because chinchilla optimal is just saying that for a given compute resource, this is, you should have data X and model parameters Y. But if you have data and you keep training you keep training larger data sets for a longer period of time, we will not get sure the compute efficiency, but for that particular model size, you will still be able to make that model better. If we fix the model size and we keep training, that was found that you can still, you can get much higher performance for that particular model size. So Quen did that at scale. Llama had also done that with the Llama in the Llama 3 models, where we found that it gave a better performance. So in some ways, you are losing, in order to minimize the inference cost, you're maximizing the, or not maximize, you're adding cost while training, but it helps reduce cost during inference. And again, like, why should they work? So how come these models being small, why are they catching up with LLMs, right? And the some, the counterpoint to SLMs catching up would be that like the generative AI field, it started with small models, and repeatedly it was found that bigger models, bigger and generalized models, which are fine-tuned on a particular task, still perform better than small specific task-specific models, right? That is something we had found. So now why do we think that going in the other direction would be better? And the second point is a philosophical point, that even like today's largest LLM is a compressed model compared to how much knowledge there is in the world. So can we really go much smaller than that? And finally, as I was mentioning, that the scaling laws are still holding. So bigger data set and a bigger model size, it should continue to show improvements. So what's missing? What is the, what is the gap? And the answer is that the LLMs they are not optimized basically in terms of efficiency or in terms of their knowledge storage. So as I was mentioning earlier, that again, pre-trained data, we know they get trained with noisy data, right? Like Common Crawl, where there is so much noise in it, and it's you can the size of data set is so much that nobody is manually cleaning the data. You do it through automated ways, and of course, the noise can and does get through those filters. The That's one. Then knowledge, the second point, and I highly recommend this paper, Physics of Language Models. Very interesting, very insightful insights here. So the authors here find that even the knowledge, so they did some experiments and finding that how is knowledge stored in how does the knowledge even get stored in these LLMs? And they found that it's not being stored in any optimized way. There are extra connections, and just the models are using much more parameters than they should. And so from an information theoretic point of view, they come to a conclusion that if an LLM has been sufficiently trained, then only 2 bits per parameter is sufficient for such a model. And what sufficiently trained basically means that any piece of knowledge is shown to the model 1,000 times at least. That is what that was the threshold that they found. And when we say exposed, it just means that let's say there is a there's a knowledge piece, say Paris is the capital of France, and that is just there in the pre-trained data many times in different ways, in different paraphrases, in different rephrases. Not the same, not exactly the same sentence, but it's just referred to in different ways. So that's an exposure. So if a model is trained this way, then 2 bits per parameter is all it should require. And then from that, they predict that in order to capture all the world and world wiki and textbooks knowledge, you should only need a 7 billion parameter model and not more than that. And that's how I like to think about it. Like, I think LLMs currently are in their brute force era. So we have, we can see like, yeah, we can throw huge amounts of data at it. We can throw huge amounts of compute at it. It will figure out algorithms. It does um, uh, mm, It does discover algorithms and very impressive ones. But now from this brute force, now we need to go to the targeted algorithms, much better runtime and much better algorithms, which are both more runtime and space-time efficient. And then finally, like, yeah, there may be some redundant or unnecessary connections. So a lot of interpretability research recently has shown that LLMs don't and they likely encode multiple circuits rather than one big circuit from start to end. So what that means is that probably there are many circuits within the model that are just either unnecessary, not being used, or redundant. And then, yeah, of course, possibly there's better learning algorithms than the transformer-based ones. So the state space models like Mamba, Jamba, they were pretty impressive. They have been pretty impressive. There have been more linear RNN-based models that are showing promise. They would be pretty good ones. And there are architectures that are optimizing the, a very costly operation, which is the matmul operation through integer addition and different ones. So I think that could be some of the ways, maybe combining them in some ways that would lead to better learning algorithm than the one we have right now. Even if we see like for DeepSeek, that was like their learning, even that was for the reasoning space, still their learning algorithm did play a part in being able to more efficiently use the resources as well, along with better training data. So then the question is, okay, what else can we do? Can we do better? And we start to wonder that, do we need a completely different way of thinking? Because let's say even if we do put these optimizations in, if the fact remains that the scale makes models better, then the energy demands will just keep increasing for the AI, right? You can now just scale it up more, scale much, more amount of knowledge, much more. So then the question is, are GPUs and scaling, are they the only way forward? So maybe not. And as I was saying that, okay, maybe like for reasoning, we have many more and more evidence that there is a different way of modeling. We need at least a mixture and not purely through LLMs, even though the LLMs also have shown emergent properties. But again, DeepSeek is a great example. Through reinforcement learning, they were able to show that they were able to find emergent properties, right, for reasoning. And maybe rethinking the hardware, rethinking the modeling techniques are the way forward for both high quality and efficiency. So just mentioning some of the research frontiers. In terms of, again, model architectures, a lot of work being done for both like at the hardware optimization level and software level. Linear models, they do show a lot of promise. So maybe that's one direction to go. Then hardware is another one, which I find quite interesting. And so like we know, right, the current GPUs or CPUs, they're all built on von Neumann architectures. In von Neumann architectures, the data and processing are separated. So which means that even for, and what that means is that every time you need to have this data access, right? Like the data needs to go to the processing unit, send back to the memory, and that consumes a lot of memory, a lot of energy. So even if we go with high bandwidth at the HBMs that NVIDIA has come up with, so even there, this will hold. You can just make them closer. Sure, we can make the data and processing closer, and maybe that might be enough. But still, the fact is that we are losing a lot of energy there. So now the newer architectures, there is research on non-von Neumann architectures where the data and processing units are together. They are the same units. And quantum computing, neuromorphic computing, they are the ones that explore these too. In fact, recently, or like last year, there was a paper published in Nature around the memristors from neuromorphic computing, where they were able to do a matmul like operation of 64 by 64 in just one tick, rather than the whole uh, quadratic time it would take. And if there is a possibility of scale, and they were able to do this for run a small CNN as well on the chip. So if there's possibilities to scale this kind of hardware, and combining it with the algorithms we have, there could be something, we may be able to build more energy efficiency while we are training. And then finally, of course, the interpretability research. One reason why we lose so much energy in ablations and experiments and trying to find the best model is because we do a lot of trial and error. And the reason we do a lot of trial and error is that we don't completely understand what's going under the hood. We understand some concepts, we understand it at a uh, higher level, that yes, okay, we see some circuits actually being formed, some algorithm being learned, but there's still a lot that mm, needs to be done under this. So that's another factor. I think the more we understand it, the more we can again learn how best we can utilize the models. Finally, if are there any caveats around this? And I would like to end it by two opposing viewpoints. So one could be that maybe like we are talking about that, hey, there is an increase in power and water demand, and that's bad thing. But maybe it's not a bad thing, right? Because it may force us to use green energy sooner. And if we have green energy, perhaps it will replace all the existing non-renewables and polluting energy sources. On the other hand, there's a second viewpoint, which is more likely that the energy, even if we build energy efficient models, that still may not be enough to um, negate or mitigate the climate risks of these models. And that's due to the Jevons paradox. So a very great paper by Dr. Sasha. And here, there's some examples of how uh, because the models are sustainable, it may just explode their usage even more, to the point that the climate impacts just didn't hold at all. Um, do recommend for this. And yeah, with that, I would end it. Thank you.
Yeah, thanks, Soumya. That was really very insightful.
Happy to take questions.
Lot of research directions and lot of insights. So thanks a lot for all those all that information. Are there any questions? I don't see any questions in the Zoom window. Any questions from anyone? Okay, in the meantime, maybe I'll start with my own question. So I think most of the techniques for reducing the carbon footprint that you mentioned, pruning, knowledge distillation, quantization, even the later ones like RNN-based architectures, I think all of them reduce the performance, right? Uh, am I right? Or
Yeah, they do reduce a little bit. The RNN ones, they need to be tested at scale though, the linear models. So I think that's the point, that is the performance degradation within the acceptable limits or not?
okay, so that you're saying that that needs to be tested, is it? That needs to be
Yeah, so the linear models have shown promise at smaller scales, but they aren't built at the ones at the scale of OpenAI and so on. So that needs to be tested there, and especially the Matmel one. But yeah, you're right. The ones that are optimizing, at least the ones that are pruning and distillation, they do degrade the performance, the accuracy a little bit.
So we just have to live with lower performance then for
Yeah.
efficiency.
Yeah. So I think one way actually to curb that is, say you come up with a model. I mean, you do pruning distillation, you have a model. Then you further align it with the tasks that you care about. So SLMs themselves, I would say they're like, more suited for specific tasks, we can get them to a pretty reasonable performance. But for a generalized model, yeah, LLMs are still doing better, just purely on the performance.
Okay, and the other question I had was, uh, so you talked about non-von Neumann architectures, right? So are they proven to be energy efficient?
They do. So, like I've not looked much into the quantum computing, but the neuromorphic computing, for example, so in the paper, they do show that they obviously they are not as fast yet, because they need to get scaled up and built a lot. But essentially, the idea is that instead of, you're not wasting time or you're not wasting energy moving the data to the processing unit and vice versa. You get to have the whole same Atmel operation in one click. And even the idea behind these architectures is that they would likely not be used just on their own, but in combination with GPUs. So you could imagine that, say or CPUs. So some of, say, the Matmel operation, which they are good at, that would be handed over to that may be handed over to these chips, but some of the other operations, like addition, that stays within GPU.
Okay. And almost all of your discussion was on energy, right? So what about water? I mean, we are
Yeah.
generally assuming that if the energy consumption is lowered, then the water consumption will also go down.
Mhm.
Is that the only conclusion, or are there any other ways to reduce the water consumption?
Yeah, that's a very good question, and that's something, like, even though the industry, they're investing in it, either with better cooling or like needing, like moving to colder places, or just doing better cooling where you don't need as much water. That seems to be the only way. Uh, Again, as Infara was mentioning, we may be able to, yes, it's true that if we are reducing energy consumption, uh, while we are training, we reduce the water consumption. But the issue is still at inference. When we do inference, then we still have the issue that we'll end up consuming, so much water, or as much as is needed for these data centers. So I think for water, yeah, that's an open problem that needs to be. I don't think there is, at least for energy, we have a solution that, hey, let's go to renewables, but for water, it's, yeah, yet to be found.
Okay. I don't see any questions in the chat windows. Uh, and we are anyway at the top of the hour, so I will probably thank you with a certificate. If this wasn't in person, we would have given you some kind of memento, but this is virtual. I wanted to share this certificate with you.
Thank
Uh,
you.
and once again, thanks a lot for this insightful talk.